All right, let's try to clarify some of the things that we said yesterday here.
What you got?
All right, how much energy does that thing have right there? Zero.
No, I have this midpoint.
It's got zero gravitational potential energy. If I move that object up to some height, h, how much energy does that object have now? Gh. Now, why does it have gravitational potential?
Because it's the Earth. I'm not going to explain it, but it's just
There's an interaction between this Earth and this object. So what we're assuming here is that we're taking the two things together as part of the system. So we talked yesterday about having two objects and they have a gravitational force between them, so they have some potential energy. But if we ignored the fact that one object was there and said this is not part of our system, then this thing by itself doesn't have potential energy. So what we're going to do some considerations here of if we take the Earth into account and if we don't take the Earth into account. What's the difference between those two situations? So if I have a mass that rests on the surface of the Earth, and I take that mass and I raise it up off of the surface of the Earth. So I'm going to move this thing from this position up to this position. And we'll call that the distance h. What forces are acting on the object as it's moving from this position up to that position?
normal force.
So gravity is acting downwards. It has a value of mg. Fp or normal force or some kind of force up. If I don't take the Earth as a part of the system, then it cannot have gravitational potential energy. Is that fair to say?
Yeah.
The interaction between the two objects causes that potential energy. If I don't take that object into account, then it can't have any potential energy. So in this situation, what we're going to do is take the Earth as not part of the system. How much potential energy does it have here? Right at the bottom. How much? Zero. So down here at the bottom, if the Earth is not part of our system, then the potential energy or the gravitational potential energy is zero. If I were to raise this up, I'm applying a force on it over a distance. The Earth is not part of our system. How much energy does that thing have? Zero. Because if the Earth is not part of our system, then gravitational potential energy doesn't count.
Okay, but potential energy. But
I'm saying if I don't include the Earth in my system, if I kind of ignore the fact that it's there, and I applied this force on it, and I applied that force over a distance, then I still have zero potential energy. There's no interaction between these two objects because I'm saying this one is not.
so physio doesn't work though.
Okay, so that's the question. I applied a force on this object, and I applied that force over a distance h. So my definition should say if I applied a force over a distance, then I should do work. And if I do work, then I should change the energy on it. But by moving it from here to here, I haven't changed the energy of it. So we have to kind of rectify this situation. How can I apply a force over a distance and not do work? And it's because there are two forces being applied over that distance, and both of them are doing work, but they're canceling each other out. The total amount of energy, total work, I guess we should say, the total amount of work, or you could say the total energy change, is the sum of all the work done, or the sum of all the energy change done by every external force. So if a force is external to our system, then it does work. Our system consists of only the ball right now. So every force acting on that is external to our system. So here is the work done. Work done by my push force, so we'll call that work by F of P, is equal to the force times the distance over which that acts. Which is h. What's the force? Oh, right, the distance is h. What's the force that I had to apply in order to raise that thing up? I had to do mg, at least mg, in order to make it go up. So the force that I pushed with is mg, and the height is h. So the work done by my push is equal to mgh. Everybody okay with that idea? That I applied a force upwards of Fp, which is equal to mg, and I pushed it up a distance h. In this case, not always. I'm saying that work most definitely is force times distance. And since I applied a force of mg over distance h, then the work is equal to mgh. Okay?
So with this working also,
This works in every single situation. And we're going to show you how that applies in different situations. When you are applying a force upwards, yes. Now, the force of the push wasn't the only force acting on it. What else was acting on it? Gravity was acting on it. So, external force. We did not include the Earth as a part of the system, so gravity is an external force. It's not a part of the system. So I've got to include the work that gravity does too. So the work done by gravity is the force that gravity did times the distance over which gravity acted. But what was the force of gravity in this case? mg, and the distance that gravity acted over? Distance h. Now, since gravity was working in the opposite direction to the way I was going, it did negative work on the system. Yeah, I guess don't text those. So the force of gravity was acting downwards. The distance traveled, or the displacement, was upwards. Those are in opposite directions. So the work done was negative. So while I was doing positive work because my force and the position change were the same direction, gravity at the same time was doing negative work. And so how much total work was done on this object? 0. Sum of all the works is the work done by the push plus the work done by gravity, but notice minus. So this is mgh minus mgh. So the total amount of energy change is actually 0. That's because we did not include the Earth as a part of our system. We do, yeah. Because the Earth is not part of our system, the force of gravity was external to that system, therefore it did work. Three dots mean therefore, yes. Sorry, question?
Oh, yeah.
This one. That's the force of gravity. Now, all of this was considering that Earth was not part of the system. So there's no potential energy here, there's no potential energy here. Now, let's look at the situation where Earth is a part of the system. We're going to do the exact same thing. We're going to apply a force upwards and make this thing go up a distance h. So we have two forces that act on this thing still. We've got the force of the push, and we have mg. Now the difference here is that Earth is a part of the system. And because Earth is a part of the system now, any forces that Earth exists are inside the system already. And if you remember from yesterday, only external forces can do work. If you're sitting in your car and you start pushing on the steering wheel, you can't make the car go. You can't do work on the car by pushing it when you're inside of the system. When you're sitting on a chair, you can't push yourself in to the table because you're a part of that chairperson system. But somebody coming from the outside can push that chair and do work on you, make you go somewhere, give you velocity. Since the Earth is a part of our system now, this force is internal to that system. It's a part of this mass Earth system. Therefore, it does no work. So when we say how much work does gravity do, 0. It does nothing because it's inside the system. Just like trying to push in your chair, you can't do work. You can try to apply forces all you want. And you can push on your arm really hard, but that's not going to make the system go anywhere. That's not going to change the velocity of the system or make you rise up. So what force is doing work on the system? FP. It's not a part of the mass Earth system. It's you coming over and picking it up. And how much work does the force FP do? Well, it does however much force it applied times the distance over which it applied it. It applied a force to mg because it has to balance out that. And it applied that over distance h. So the work done by the force of the push is equal to mgh. Any other work done?
0.
Work done by mg is 0, so that's the total amount of work done. So how much does this object's energy change when I raise it up to that? It changes to mgh.
It's all off perspective.
Right. You have to consider what thing or things are a part of your system. If they're a part of your system already, they can't do work on it. So you really have to be careful about what you include as a part of your system prior to the problem starting. or make sure that you're answering the question that the problem is asking. Only when we have an interaction between two objects do we end up with potential energy. Because only with those two objects interacting do we end up with some kind of net work done, and therefore a change in energy. Maybe? Makes sense? Yeah. Questions about that?